Thanks, Yaseman, for the introduction, and welcome everyone. Um, we'll get started, and I'll start with a bit of some hardware details. So just to give you like a very high level overview of Polaris, this is our latest computational resource. The machine's relatively new. We started running it in around July. It's currently generally available, so current insight or new insight proposals were able to request it. I believe there's some ALCF proposals using it. And if you're just looking to try to submit a request for one of those in the future, we always have the director's discretionary that you can request. And you can see that I put from the latest top 500, Polaris landed 14th on the list. So it's pretty good. Its HPL score was 25.8 petaflops. So it's a reasonably good machine. And well, now this is what it looks like with its skin on. So I'll give you some details about the hardware. So this is kind of on the right, a notional drawing of what the node architecture looks like. So I'll just kind of hit some of the highlights here, and then we'll go into some more details of each component. So each node is a single AMD CPU. It's directly connected to 4 Nvidia A100 GPUs. So the connections to the GPUs are PCI Gen 4 with 16 lanes, but then within the GPUs are all connected via NVLink. And so you can see down here, there's a large aggregate bandwidth between the GPUs. So we've got 600 gigabytes a second aggregate between all of these. So any kind of data movement between the GPUs is quite efficient. The system also has 2 NICs. It's currently, for those of you familiar with HPE Slingshot, there's various flavors, and so we are currently running what we call Slingshot 10, and so it uses these Mellanox CX5 NICs. And so at various points in the presentation, you'll see some certain network things labeled with SS10 or SS11. So the future these will be changed to HPE Cassini NICs, but currently they're the Mellanox CX5, so that's what I'll focus on. So those provide 25 gigabytes of injection. We also have some node local SSDs, so I'll touch on those a little more later, but this is a general node architecture. So now if we look at the CPU, this is, what the AMD codename Milan series is. So it has the Zen 3 core. See, the frequency is 2.8 gigahertz, so it's reasonably good single thread performance. It has 32 total cores, and we do have the hyper-threading turned on, so you'll see, a total of 64 hardware threads possible. We have a relatively large amount of memory per node, so 512 gigabytes, so you can fit all of the GPU memory easily in the CPU memory as well. And then, as I said before, we're using these PCI Gen 4 lanes for connecting to the GPUs. Now to look at the NVIDIA A100. So in these 2 columns, the Polaris is using what, if you see on the lower right here, NVIDIA calls this the Redstone board. So it's a board with 4 GPUs on it. That is what the most right column has. It's an aggregate of 4 GPUs. And the center column here is just for a single GPU. So I'm just going to kind of talk about a single GPU. But of course, your codes for each node, you'll have full access to all 4 GPUs. So for normal double FP64 pipeline, you've got 9.7 teraflops of performance. But if you can utilize the tensor cores with, matrix operations, then you get, twice the efficiency. So you can get almost 20 teraflops out of each GPU. Then, of course, for lower precision, you've got significantly higher performance possible. Also, we are running the 40 gigabyte flavor of the A100. Currently, like if you were to go and get an A100 today, it would be 80 gigabytes, but Polaris is using a slightly older version. The compute side is all identical. It's just the amount of memory. So we have the 40 gigabyte HBM2 versions. You'll see you've got 1.6 terabytes per second of memory. It's kind of like a single GPU in a nutshell. And like I said, you'll have the combined power of 4 GPUs for every node. For the node local storage, If you've used our Theta system in the past, it also has no local storage. This is very similar. Currently, we have each of the SSDs configured in a RAID 0 volume. So we should see the total 3 terabyte capacity and get slightly better performance. So you're using both SSDs at the same time. And it's mounted under local scratch. And as previously on Theta, we don't have a specific software stack. So like you would just access this through POSIX APIs. And if somehow you want to share data between two different nodes, you would have to develop the software to, copy data between the different node local storages. And then this data is destroyed when the job ends. So if you want to keep any of your data that you've put on local scratch, then you'll need to copy this back to one of our other file systems. Now we'll go a little bit more of the high-speed interconnect. So like I said, this is HPE Slingshot. There's two flavors. One is called SS10 and one is called SS11. Eventually Polaris will be using SS11, but it's currently based on Slingshot 10. So we have these 100 gigabit NICs. So you'll see our injection is 14 terabytes a second, while the bisection is 24 terabytes a second. And when we go to SS11, you'll see our injection will double when we increase the NIC speed. The Rosetta switch, some of these features are active, but some of them require SS11. So for example, some of the QoS requires SS11, which we don't currently have. So most of this is off, but the adaptive routing and congestion control for controlling the latencies, that's all active currently. And of course, on Slingshot 10, you can still use the Cray MPI. This is essentially running the NICs in Ethernet mode, and it does feature RDMA. For those familiar with Dragonfly, the Slingshot is based on a Dragonfly topology. So essentially you have 3 hops generally between any 2 points as the worst case. Unless you start to go indirect routing, then you can have more hops. And so the NICs are connected to the switch by this 100 gigabit link, but then all of the inner switch links are all 200 gigabit. And so on Dragonfly, we have level 1, which is these green links. So each switch is connected to each other switch within what we call a group. And you'll see that on the compute side, Polaris is composed of 10 compute groups. And then there's one service group, which contains all of the other administrative nodes as well as the gateways. So any IO exiting the system is going to be exiting through the service group through one of the gateway nodes. These red links define the global links between groups. And so, for example, if you have a job that's spread out among multiple groups, you may be using some combination of green links and some combination of red links. And so a job with let's say 50 nodes, better to be spread out across because you can maximize your use of the global bandwidth. But let's say a small job, it's better to be compact inside a single group, so you can just stick to using these red links, which usually minimizes your congestion and maximizes your bandwidth. Now, just to give you some aggregates for the whole system. So we do have a total of 560 nodes on Polaris. Not all of those nodes, you cannot run currently a job using 560 nodes because not all 560 are in a single queue. So I'll talk more about that later, but we do have a total of 560 nodes, which gives us a total of more than 2,000 GPUs. So this is a great platform if you want to scale up to the next level of exascale machines. You can start running with a large number of GPUs. And then finally, Polaris doesn't have any dedicated storage system other than the node local storage. It uses all existing storage that we have for the rest of our system. So if you already have an ALCF account, we use the same home file system. So when you log into Polaris, you'll see the same files you have. If you haven't used ALCF systems before, your home will be for Polaris, but if you do use another resource like one of the visualization resources, you'll have a shared home. Then we have 2 main file systems that are both Lustre based. And those are center-wide file systems. They're generally identical. So you can see they're each 100 petabytes at, let's say, nominally 650 gigabytes a second. With the main difference being Eagle has some additional capabilities for Globus to do community data sharing. And as I said before, these are connected through LNAT routers. So by design, we have 50 gateway nodes that can provide more than 1 terabytes a second access. So you should be able to maximize the bandwidth of any of these file systems. I do have to say currently, due to some supply chain problems, not all of our gateway nodes are actually connected. So we're missing the proper cables to connect all nodes. So our current bandwidth is a bit limited. So if you did some IOR benchmark testing, you might find that our performance is not as high as it should be. Eventually, this will be corrected and all of our gateway nodes will be fully cabled into the switch network. So that's a general overview of the hardware of Polaris. If there's any questions specific to hardware, let me know. Otherwise, I'll transition over into some software. All right, there's a question in the chat. Okay, so someone's asking about getting the network topology. That's currently an open question. So each node has what HPE calls an X name. And so your X name represents your physical location in the network. And so you could take any two given nodes and look at their X names and then know, okay, are they in the same group or not? Are they the same chassis or the same blade? And so you'd understand at least somewhat of the topology. But there isn't yet, although it's on HPE's list of things to provide, a function that will tell you, okay, this is the distance between two nodes in some relative units. So I hope that answers the question, but it's currently, we don't have said MPIX interface yet.
Kevin, I don't know if you get a chance to answer the information that Kaushik is asking about distance between ranks.
Yeah, that's what I was trying to address. We don't have an exact answer to these yet, other than, as I said, you can decode the X name and get some information about its location and then decide based on that where things are, except we don't have a nice interfaces as BGQ did with a MPIX call that will give you that information. So that's still on HPE's to-do list.
Okay, and then there is a comment from Alfred that is asking about the blue L0 link. I don't know if you've had that in your slides.
Oh, yeah, sorry, the level zeros, that was the first thing I started, which is the NIC to switch connection. So the NIC, it's considered level 0 as the NIC connecting to the switch, and this is connected at 100 gigabits. So in the future, when we go to Slingshot 11, this will be 200 gigabits, and then this will be fully balanced.
Thanks. Do you have a timeline for when we go to the Slingshot 11?
Yeah, we think it'll be end of the year. So if you start running on Polaris soon, you'll still be for several or multiple months running in this configuration. So I think it's reasonable to know that it'll be 100 gigabit.
Thank you.
All right, then I'll transition over to software. So to start with, to use Polaris, you need an ALCF account. You can go to accounts.alcf.anl.gov to request one. You'll need a project. If you don't have a project, then you'll need to first request a project, and then the resource you request is Polaris. If you already have a project, then you can just go and request the Polaris resource for that project and get some additional hours there. Once you have your ALCF account, you can log into Polaris by just using your ALCF username and going to polaris.anl or alcf.anl.gov. That will land you on one of the round robin. It'll pick one of our front end user access nodes. And then the password, of course, is your PIN plus your one-time password. For file systems, again, as I mentioned, we have a shared home. So /home will be the shared with the other ALCF system. So if you already have an ALCF account, you'll see all of your files there that you had before. And then typically you should have a project defined on one of these two file systems, either Eagle or Grand. We do not mount the older Theta FS0 system on this because on a completely different IB network. So if you have data there and you want to use Polaris, you're going to need to you should already have a Grand or Eagle project space. But if for some reason you don't, or you don't know it, you can ask support for like, what's my project space on Grand, and then you'll need to copy your data into there, and you can use Globus to help you copy data between those two endpoints. So for example, if you're Grand, less Grand projects, your project name, and that's your main storage system. And, obviously, like I said, if you have Eagle, if you've designated your project as some kind of community project, it'll be on Eagle, and it'll be in here as well. The first thing I suggest when you get on the system is you want to use this module avail command. This will list all of the software that we have available on the system installed. There's multiple pages. So since Polaris is new, this is always changing. So it always, at least currently, if you're looking for something, always take a look in there because it's likely being updated over time. For those not familiar with modules, it's a set of commands that will help you add things to your environment to help you build things. So we use the LMOD variant of modules, and it's designed to interoperate with Crae's compiler wrappers. So for example, this is a current default list that when you come on the system. And so if you use the CC wrapper, I'll discuss this more in detail later, but and you load this particular module, it will select the type of compiler and what libraries get linked and so on and so forth. And so if you want to roll everything yourself, you're free to do that, you can. But if you want to make your life a little bit easier, you can just load modules using module load, or if you don't want a particular module, you can unload it. And this will affect the behavior of the compiler wrappers of what you're linking in. So compiling. So we have the Cray programming environment. So if you've used any previous Cray machines, you'll probably be familiar with this, but if not, it's a set of wrappers that are called CC for C code, uppercase CC for C++ code, and FTN for Fortran codes. And if you use one of these, it will you can select a particular compiler. So our default is NVIDIA compiler. So for example, if you use uppercase CC to compile, it will call the NVC++ compiler. It will specify all the options that were set by the modules before, and then all the various linking libraries. So MPI will already be linked in by the wrapper, so to speak. And so this will generally make your life easier. If you want to know what the wrapper is doing for any of these, you can always add the flag CrayPE verbose. This will cause it to print out the exact compile line. So you'll see all of the details of all the switches, paths, and libraries that are being added. If you're a GNU user and you would prefer GCC, you can always switch to this module. So you can say module swap programming environment NVIDIA to programming environment GNU, and then the compilers will change to the GNU ones. Let me also step back now that I covered that a little bit to hit some details. First, you'll notice we have the CrayPE x86 Rome module loaded. So as I said before, the systems are using Milan CPUs, but there's some negative interaction between currently the version of NVIDIA compilers we have loaded, and it doesn't quite understand all of the Milan instructions. So we stick here to Rome currently. If for some reason you wanted to build some CPU code yourself, and you could load the Milan module to get the more optimized code generation for the Milan. Another thing I'll point out is currently there's kind of a transition period in naming. So there's a programming called Programming Environment NVHPC and one called Programming Environment NVIDIA. Those are identical. They're the same thing. They're just two modules with different names. NVHPC will be the name going forward. They'll be phasing out the NVIDIA name. And then we also have this module loaded here that provides specific architecture optimization for the SM80, as well as turns on some of the peer-to-peer copy function capabilities and hardware acceleration. So then how do you run a job? So you'll need to, similar to most systems currently, have to write a shell script. This script will be run. and then you'll need to launch your job with MPI exec. So if I kind of just walk around this example I put on the right, you'll find some script. You can put the options for the scheduler in here. So we're using PBS. So if you put, pound PBS, these options will be interpreted by when you submit the script as options for Q sub. So required options, you need to have the project you'll be using. This is specific to your project. Need the wall time. And I'll go through, we need to have various wall time requirements. So you need a wall time, and then L-select equals 4 tells you how many nodes you're picking. So this would be, I want 4 nodes. In the case of Polaris, you will always have all GPUs, all CPUs, like all resources of the node are exclusively yours. So you can just put select and the number of nodes you want, and you'll have all resources. There's other options you can do, and I'll mention some of those to make this fancier, but this just will give you the exact number of nodes you request.
Kevin, I have a question. So if you do select 4, it gives you all the GPUs. Can you select like only 2 GPUs, let's say out of 4 GPUs or something like that?
Currently, like you could put N GPUs 2, however, you would still have access to the other 2 GPUs on the node. So in order to limit your access to the other GPUs, for example, if you were doing some scaling test and wanted to do that, you have to use the CUDA visible devices environment variable to control that.
Okay, and I think we have a lot more description in the website and documentation. Is that correct?
Correct. Yeah, and I'll mention some more options that are here and go through that. But yes, we do have several examples. I have noted the links later on for scripts. There's this option called L system equals Polaris. Currently, if you leave that off, that's okay. It doesn't have any effect. But in the future, if this scheduler is able to schedule multiple resources, so for example, some other system, you need to differentiate where you want your code to run. So this is what you can put. So if you want to future-proof your scripts, you can add system equals Polaris. And then finally, also not a requirement, but an assumption will be made if you don't select it, is adding L file systems equal and what file systems you require to run your job. So for example, if I need home and I have my project based on Eagle, I can say home Eagle. If at any time the Eagle system is down, or this job won't run. So it'll be like, oh, Eagle system is down. This job depends on Eagle, so I won't run it. If, for example, Grand was down, but Eagle is up, well, this job will be runnable since it doesn't depend on Grand. If you don't specify this, it assumes all file systems. And so then anytime a file system is down, your job will be paused. This lets us upgrade one or the other file systems without taking all jobs offline. So it's definitely useful to you if you correctly specify these in your job. Oops, sorry. Next, PBS has many variables. You can look some of those up, but there's a node. So if you want to just compute the number of, let's say, processes your job will have based on the number of nodes that your job came with, you just can do some math here. Another thing that is different from how our previous scheduler worked, Cobalt, if you're familiar with that, but depending on which schedulers you use, this may or may not be different. But your job will run from essentially like a root directory or your home directory by default. So if you want to run from where you submitted the job, if you want the behavior of, oh, I was in some directory and I submitted from that directory, I want that to be the working directory of the job, then you can add the cd $PBS o worktor, and it will then change to wherever you had submitted the job from. So for ALCF, our previous scheduler, that's how it worked. So I think most people who are familiar with our system probably would like this to add this. But if you don't care where it's run from, you're using absolute pass everywhere, you don't need to have this. Then depending on if you were relying on non-default modules, you need to load those modules. So you need to put module load, whatever the extra modules that you were using that are not default. I always suggest if you want help from support, it's good to put this set command in here to turn on printing out what commands were actually executed. So when I put this in, when I see in my standard error, I won't see this line that says $procs. I'll see how many processes, how many ranks per node. All of the variables in here will be expanded. And so that makes it easier to spot if there was a problem with a path computation or something like that. You'll see what the variables expanded to. Also suggest it's convenient to put the env command that will dump out the environment that your job was running on. So if you thought something should have been there, but it wasn't, or maybe the LD library path is wrong, you can go and you'll see what the environment of the job is running under. Again, this can help debug various issues. And then finally, you need to launch a job. And so I'll go into more details of MPI exec, but you'll launch MPI exec and then run your whatever your binary with the options. This also slightly different than from our previous system, runs on one of your compute nodes. So this script is executing on one of the compute nodes in your job. That means if you want to do some more computationally heavy work in this script, it's your node, you can go ahead and do that. No one's going to yell at you. These resources are yours for your job, so you can go ahead and do that. So if you want to do some kind of computation before or after the job and just run it on this node, that's no problem because it's running on one of your compute nodes. And finally, to submit this, there's one last argument you need, which is to queue. And so you can also put queue in this list. And of course, if you do put anything here, you can always override those on the command line. So q sub dash q prod and then the script name. And again, all the logs will go to where you submitted, but unless you do this, the job will run from the root. And so that may or may not be what you want. So again, I suggest putting this unless you are happy to use all absolute paths. Okay, next, we'll look a little bit more at the scheduler and some options you might be interested in. We also support interactive mode. So if you want to use a debug, you can use -I and then you'll run interactively. So basically when the job starts up, you'll SSH to one of your nodes. And then from that node, you can run commands or call MPI exec, whatever you need to do. Also, if you, on this system, we have multiple queues. I'll go through some of those, but if you do qstat -Q, you can see a list of all the queues on Polaris. If your job has been submitted or is running, you can use qstat -F and the job ID to get detailed information about the job, like where it's running, like the nodes that were allocated, how long, a bunch of information about your job. If your job has ended, so whether it ran successfully or not, you can use qstat -X and give the job ID, and that will then tell you what this information was for a previously completed job. And so that's handy if you come back to the system and you want to see, let's say, which nodes were allocated to your job or any other information about your job. You can use qstat -X to look that up. You can use qalter to update any of the options while the job is still queued. As well as you can use qdel to delete a job that hasn't run, but also a running job if you're like, okay, there's some problem with this job, I don't want to waste any more time with it. qdel, give the job ID, and that'll send a kill signal to the job and it will exit. A few more details that we were talking about, the select statement. It's quite complex. You can put a lot of features in here. We do have references on the ALCF documentation that go into you redirect you to the PBS documentation. You can see how to use these, but you can specify like, okay, these 3 nodes will have this information, or this is the exact node I want to run on. So I can put the exact nodes I would like in this list. Obviously, the more detailed information you put in here, the possibly longer it takes to submit your job since you put more requirements on it. And then we do have defined, they're listed on the ALCF documentation, jobs groups. So for example, I want to run in group 0, you can put group 0 here, or if I want to run in group 2. So if I want 32 nodes from group 0 and 32 nodes from group 1, you can specify that. So there's options for this those are called V nodes when you're specifying the specific node. And then there's this NCPUs, NGPUs. As I said, currently Polaris gives you all hardware. So you can, if you put NCPUs equal 32, you still have 64. Or if you put NGPUs equals 2, you still get 4. So these don't, you can specify them, they're fine. They just don't currently have any effect on the system because we run the nodes in exclusive mode. So you have full access to all hardware on the node. A few other commands. If you used our previous systems and have COBOL based scripts that you would like to bring to Polaris, there's this tool called qsub to PBS that will take your previous scripts and then do its best to convert the variables and the arguments to PBS arguments. And so you can do that as a first pass to get your script and then tweak it from there to run on Polaris. If you don't know what I mean when I said Cobalt and have no idea what this means, like, yeah, you can ignore all that. Don't worry about it. The last command, there's called PBS nodes. It will list information about the nodes on the system. And so if you want to get current state information about specific nodes, like how many nodes are idle or things like that, you can use PBS nodes. It's a little bit similar to node list if you used our previous systems. All right, now queues. So you need to specify a queue, and knowing which queue to use is important. And then there's rules on each queue. And so I put the link in here. You can go there, read about the queues. There's 3 main queues. Versus debug, you can request either 1 or 2 nodes max. The max wall time you can ask for is 1 hour, and the minimum runtime is 10 minutes. We usually put a minimum runtime in for most things just to make sure that there's enough time for the job to start and you don't get some kind of timeout before the job actually starts up. So if you just use 5 minutes of runtime, that's fine, but you need to put 10 as the minimum runtime. Otherwise, it will reject your request. There's also a debug scaling queue. This will let you run up to 10 nodes and with the similar constraints as to debug, but with more nodes. And then finally, there's the prod queue. This is the main queue that we expect most people to be submitting unless you're debugging. And so it does require 10 nodes min. So unfortunately, you cannot submit a like 6-hour 2-node job. We expect if that's the workload that you need to run, that you should be running that on another system, as Polaris's main goal is to run a large scale jobs. So currently right now, the min size is 10. The max size is 496. So as you said before, I told you the system has 560 nodes. The most you can run on at one time is 496. So be careful of that, that's going to be your maximum nodes you can run for one job. And here there's a 30-minute minimum for running. And then the maximum actually depends on the exact number of nodes you pick. So there's 3 kind of classifications of small, medium, large. So if you're, this all information is on this guide. I just didn't reproduce all of it in the slides, but depending on if you use like, let's say 20 nodes, you're going to be a 6-hour max wall time. But if you have like 60 nodes, you'll be in a 12-hour runtime. And then I think if you're more than 100 or so, you'll be in a 24-hour max wall time. So if you're running a large scaling job, you can run at most 1 day. And the way this works is prod routes to other queues. So for example, if you look for which job your queue is in, you may see it's not in the quote unquote prod queue, it's actually in the medium queue. And that's just because you don't submit directly to the medium queue, you submit here, depending on your arguments, and then submits the job to one of those other 3 queues. Like I said, there's far more details in the above. So then the last component is running actually MPI. And so the HPE system uses its own parallel launcher that they call PALS. So when you run something, you're using what's called PALS run, but there's a wrapper for MPI exec, so you don't need to use the word. You could use PALS run directly if you like, but you can use MPI exec. However, this is just a wrapper, and it's not MPI exec as in from MPitch or OpenMPI, so it's got its own unique set of arguments that may or may not be similar. So you can look at the help or check the man page, get more details, but I've just put the kind of the basic ones. which is total MPI ranks and then how many ranks per node. If you want the CPU or your processes bound to particular CPU cores, which we definitely suggest because the AMD has processor has some various NUMA effects, so definitely recommend CPU binding. Then, of course, if you do that and you want to skip over thing, like if you're not using every core or a hardware thread, you can use depth to skip over some. So how many CPUs per rank you should have. If you need to set any environment variables, I believe the default is that it will take all of the environment variables and put them in the global environment, so every rank will have access to them. The -G, E, and V all is what controls that. But if you want to add specific environment variables, you can. And then again, you can specify the host file, but that it knows where the host file is by default, so you don't need to specify that unless you want to. And as Yasmin said earlier, on this webpage here, we have several JavaScript examples showing you different combinations of using these. So I suggest looking at that if you want to do, especially if you want to do something more complex, take a look at there. Here, for controlling MPI or behaviors of MPI, the HP system has many variables, like hundreds. So you can do man MPI intro and kind of scan through this list. You can search for the things that you might want, but you can do rank the process mapping. You can control GPU, MPI behaviors, so on and so forth. So more than I can show on this page, but it's well documented, so you can look through this if there's any various tuning that you want to apply to MPI. You will find it in this man page. Now Python, so I'm just going to hit a quick highlight. Sam is going to go into more detail, but the Create PE provides a basic Python. The module is called Create Python. So if you load that, it's handy in that it comes with NumPy, SciPy, Pandas, MPI for Pi, maybe a few other things that can get you off and running. This, however, is only for the CPU. NumPy does not offload to the GPU in this module. So if you want to do actual computing, Sam is going to tell you how to do that. It is not using this. This is good if like you just need a control system and like all your library code is perhaps like you just need Python to call your libraries. This would be perfectly acceptable, or you need to do something very basic, pre or post processing. This is handy. But if you want to do actual computing with Python, then hold all your questions for Sam. Finally, we do have a few debuggers and profilers. So stat is available on the system. It's currently having some issues, so if you try to use it, it may not work. We have an ongoing debug with HPE on this. HPE also provides a tool called GDB for HPC. It's built on GDP. Its interface is slightly different and it behaves slightly different, but it does let you step your whole parallel job. We have CUDA GDB, so if you need to debug something specifically on the GPU, you can use CUDA GDB. And then a generic GDB that's just a generic Linux install. On the profilers, this used to be called CRAPAT, now it's just called PAT, but it's a whole system, whole program analysis, so it'll give you a breakdown about MPI and time spent on each rank. You can get load balance information. It generally does not give you details about GPU performance, though this might just be an aggregate. So if you want to do GPU performance analysis, then you want to use NVIDIA's Nsight, which we also have.
Kevin, I think there's a question about MPI run, and I wonder is MPI run and MPI exit are the same or a different thing?
Correct. MPI run wrapper is also available. So if you call MPI run, it's just the same as MPI exec.
Thanks.
Okay, I see there were some messages in chat. I don't know if I've covered those or if there's any.
Yeah, they were answered. The last one was just, does MPI run work?
Okay.
So, yeah.
Well, there's a question from Silvio and about
Go ahead, Silvio.
running containers.
Okay. You can run containers. I don't know, Sam, were you going to cover running containers?
Yeah, I see the question. And you know, I have a couple slides on it briefly, but I'm not sure that I answer this question. Silvio, if you want to reach out on Slack, we can, go through it in a bit more detail. I think Corey Adams probably might be the person to ask about detailed questions about the containers.
Perfect.
Yeah, so-
Yes, will do.
So looking at the chat, Silvio, you're asking about if you have an MPI inside the container. Is that correct?
No, it's actually how to dynamically link to the native version of MPI from the container, right? To get the maximum performance of the network.
Oh, okay. So when you do a container build, how do you make sure that you specify?
Correct.
Okay. Yeah. I think that's a detail that we can't explain here, but yeah, we can come back and make sure we add that to the documentation.
Perfect. Yes, will do.
I'll hand it over now to Sam, but I just want to make again a general pitch for our documentation. It's been in development, so it's always being updated. So if you looked at it originally and maybe didn't see something, look again, because we're constantly adding to it. And of course, if you need any help, you can always contact support@alcf.anl.gov.
All right, I will go ahead and share my screen. All right, hopefully everybody can see it now. Move these out of the way. All right. Yeah, so this should, this is probably, there we go. Okay, yeah, so this will be somewhat brief. And again, this is mostly just pulling information from the user guides, and there's also a corresponding repo that should have, it's not, I don't think, fully stocked at the moment, but once this is more up to date, there should be example scripts that can go over all of the content linked to and described in the documentation. So at a high level, I'll be talking about using Python on Polaris and working with default Conda modules and how to expand it and customize it for your own needs. So the kind of starting point is the built-in Conda module. And so this Kyle Felker actually is responsible for a lot of this, has done a lot of this work, and so really deserves a shout out, and has been the one responsible for building all of this and keeping it up to date. So it's been a huge help. And again, there's additional information on all of this in the user guide, but some of just the high level snippets that are probably important to most people. So there's a base Conda module, which can be loaded just using this module load Conda and then activating the Conda base environment. And so this comes complete with GPU supported builds of PyTorch, TensorFlow, most of the machine learning libraries that people would need or would want to use. If there's something that you want that isn't included in the base environment, if you send a message to support, we can more than likely get it built and put in there for you. But you can also start with this base Conda environment and customize it to your own needs. So the easiest way of doing that is using a virtual environment. So you can load the base Conda module and activate the environment, and then on top of that, create a virtual environment that sits kind of on top of the base Conda module. And so this can be done just using, Python-VNV, specifying the path to the virtual environment that you want, and then passing the system site packages flag. So this basically tells the virtual environment to use the system site packages that are already installed from Conda. And so you'll have everything available in the base environment inside this virtual environment as well. Once you've ran this command to create the virtual environment, you can then activate it by sourcing this activate file, which lives inside of the virtual environment. And then once you've activated it, you can check and make sure that you're using the right Python, and it should spit out the path to the virtual environment that you just created. And once you're kind of inside and have loaded this virtual environment, you're then free to pip install any additional packages you might need. Some kind of warnings or things to be aware of about this. So you want to make sure to include the system site packages flag, because that tells the virtual environment to use the system packages which are installed by Conda. And you also obviously have to be careful about where you specify this path, and you need to be somewhere that you have write access to, obviously. And so if for some reason you forget this system site packages flag when creating the virtual environment, it's useful to know that that can be changed by, just editing this py-vnv.config file, which lives inside the path that you specified in your virtual environment. So that can be changed if for some reason you forget it, which is useful to know. You don't have to go through the process of recreating it and everything. If you, for some reason, want a different version of a package that is already installed in the base environment, you can tell pip to explicitly ignore previously installed versions, and this will kind of take precedence in the order, in the order in which they are found. So this will install it on top of the other version that you don't want. Another kind of nice thing to know about this is that the base environment is not writable, so you don't have to worry about accidentally, changing something in the base environment and breaking things for other users. But it does happen occasionally that there are packages which you need to install which are not provided in the base conda module and are not available through pip install. And so in that case, you can, instead of just using a virtual environment, you can actually clone the entire base conda environment. So this is useful, again, as I said, if you need additional flexibility or to install packages which require a conda install. So I think like CUDA toolkit and certain other things need to be installed with conda. And so in that case, if you have something that needs to be installed using this method, you can actually clone the entire base conda environment. The steps for doing this, again, are just first loading the conda module and then making sure you activate the base conda environment. By default, I think it should change your bash ps1 variable, so it'll give you a little confirmation that you're actually in the base environment. And then to create a clone of that, you can just pass this command. So conda create clone, we want to clone the base environment, and then you can specify a prefix. Again, you have to make sure that this is a path that you have write access to, and that'll essentially tell conda where to install this clone of the base environment. Some things to maybe note about this is that this is it takes a while, just because there is a lot of files that actually need to be copied and everything. And so this also gets to be pretty cumbersome. That is a pretty large storage requirement. And so it's recommended to try to use a virtual environment when possible, just for, the sake of it being easier and less, compute intensive, less memory intensive. But obviously this is also not an additional option if you need the additional flexibility. Yeah, so we also offer containers on Polaris. So the default container package is Singularity. There again, there's much more thorough documentation on the user guides for doing this. But it is useful because you can use, so Nvidia, for example, builds Docker containers, which are optimized to run on Nvidia hardware. And so we've actually, in some of my applications, we've gone through the process of converting Nvidia optimized Docker files and gone through and built them as Singularity containers. In the process, again, the documentation for doing all of that is available online. I'm not going to go into too much detail about it, but there's a Singularity module which is available. So either from a interactive session or inside your job script. Well, I guess the available command would only be useful in an interactive environment, but you can look at all of the available Singularity versions by using this module avail, as Kevin touched on previously, and then load it using this module load. Again, there may be specific versions, and so if you're looking for a specific version, you can always load that specifically. There are two main options for creating containers on Polaris. The first being either using Docker on your local machine and pushing the file to Docker Hub, or alternatively, you can use a Singularity recipe. You can use a Singularity recipe file, which can be made from a Docker file with minimal, I would say minimal effort. Sometimes there's some minor complications, but for the most part, that should be usually pretty painless. And so you can have this Singularity recipe file that you can then build the Singularity container on the worker node directly. And again, there's much more information than I could fit into these slides available on the user guides for those who are interested. Again, just, for the sake of time and not being able to include everything there, we support all of the modern machine learning frameworks in this base Conda environment. And there's a host of, a bunch of general tips and best practices for using the different frameworks available in our user guides. So as you can see, JAX, PyTorch are all available. And this should be deep speed. So they're all supported and included in the base environment. So you should be able to get up and running with those with minimal effort. And yeah, there's a bunch more detailed information on all of them in these user guides, and the getting started repo should also have, there should be a one-to-one mapping between the different frameworks and example Q subscripts in this repo. So make sure to, again, as Kevin said, this is all kind of in flux, and it's being updated pretty continuously. So if there's something that's not there, make sure to bring it to our attention and we can try to get it updated as quickly as possible. I see that I'm running pretty quickly out of time here, so I'll kind of go through this stuff, the next a bit quickly. So again, as Kevin mentioned, yeah.
If you want to take like maybe 10-15 minutes extra, that's okay.
Oh, okay. All right. Yeah, so, I really am, this is really about it. So I have this bit on the debugging tools, which Kevin actually touched on previously. This is all, again, in the user guides for, much more detailed, but the main debugging tool on Nvidia is this CUDA GDB, which, is a debugging tool built by Nvidia. So it does a lot of what you would expect from the debugging applications. Maybe one thing, so now I guess I do have a bit of time. So this has some instructions for using Jupyter notebooks on Polaris. So the official ALCF Jupyter hub, I don't think is set up to run on Polaris quite yet. I know that that's something that's in the works, but in the meantime, you can, if, for example, you really want to run a Jupyter notebook on Polaris, that can be done pretty straightforwardly. Again, you just need to load the base Conda module and activate the environment. Once you're in that, you can then install this IPy kernel. Again, I'm not sure, this might be already pre-installed, so some of this might be a bit redundant, but for the sake of completeness, all of the instructions are here. So this will install this IPy kernel, which is a library that allows IPython allows the Jupyter runtime kernel to connect to the Python that you're using to launch it. Once this is installed, you can then create a kernel using the Python that's currently active in your environment, and you can give it some name. Once this IPython kernel is installed, you can then launch a Jupyter notebook. And one kind of pain point of doing it this way, instead of having it being worked through the Jupyter hub directly, is that you need to manually specify the port that you want to use. And then, you can just write the output to somewhere in temp so that you can see it if you were to need to. Another thing that I know this is maybe a bit involved, but for those who are really feel like digging in a bit, the two things that are important on the slide are making sure that you know which port you specified and the host name that you're executing it from. So for example, this is one of the worker nodes on Polaris. And so in this example, if you specified port 8899 and you have the host name specified here, you can use port forwarding to basically connect your local machine to the compute node running the Jupyter instance. So the first step would be starting from your local machine, specify this tunneling flag. So you want to SSH, set up a port forwarding from your local host using whatever port you specified on the previous slide to your local host, and then to the port, or using the port to the Polaris login node. And this will basically create a tunnel between your local machine and the login node. And then you'll need to do that again to connect from the login node to the actual worker node running Jupyter. And again, follows the exact same format. You just need to replace the login node here with the actual worker node. And this will basically connect or complete the circuit, right? So you can go from the local machine to the login node to the compute node, and it basically completes that loop. And then from there, you're basically all set. You can then just hopefully connect to, if you navigate in your local and on your local machine in a web browser to localhost 8899, it should pull up the Jupyter interface and you should be able to run straight from the compute node. Again, so this is all a bit involved, and this will probably be deprecated pretty soon once we've gotten the Jupyter hub connected and working, but in the meantime, is kind of a workaround that I've found personally to be useful, and I thought might be useful to some other people who, are interested in diving into some of the details. One kind of warning about using this approach is that, this is probably not a best practice either, but only one port can be used at a time. So in this example, I used, 8899. And so that means anybody else that were to try to follow these instructions directly would run into an error, since only one port can be used at a time. And so if you run into this, you'll get a bunch of errors in the Jupyter output. And so I don't know if there's a systematic way of fixing that, but one way to just randomly try a different port. Obviously, that's not ideal. And again, this is this is a bit of a hacky workaround, but for those who are daring and really want to dive in. So yeah, that's really all I had to say. Really, that should cover the most, a lot of the basic use cases, and should be enough to hopefully get people started. Obviously, if there are any questions, feel free to reach out offline. I'd be more than happy to address and try to help however I can. So yeah, that's it. I haven't checked the chat. Are there any questions?
I don't see any questions, but thank you so much, Sam. So are there any questions for Sam or Kevin?